Hi, this is Dane Quinn from the University of Akron, and for today's lecture I would like to discuss eigenvectors, and in particular some of the properties that they have. And this is for fundamentals of mechanical vibrations. So I'm going to start off with just kind of a background introductory slide. This is taken from a lot of the video lectures that I've recorded earlier. So if you've watched those, all of this is not new. If you haven't watched this, well, it might be new, and I would urge you to go back and watch the old ones. So we're looking at general, unforced, conservative, multi-degree of freedom systems, right? So we write them in the following way. We have a mass matrix M. We have a coordinate vector x, right? So x double dot is the acceleration vector, plus a stiffness vector, or a stiffness matrix, k, times the coordinate vector x equals 0. Again, unforced, general linear system. And of course we have initial conditions. Now, just as an example, I have drawn here a 2-degree of freedom system represented by 2 blocks that are connected with springs, so essentially a chain of masses that is fixed at one end on the left and free at the other. Of course, we can go through and derive this using momentum balance or Lagrange's equations, and we might get equations of motion that look like this. Mx double dot, again, x is the displacement of the first mass, and then here we have stiffness terms from the left and the right spring acting on that mass, equals 0, no forcing. M times y double dot, so sort of mass times acceleration, and then this represents the force acting on this mass, which of course is dependent on the relative displacement between these two. So from this we can identify a mass matrix that takes the following form. Here it's actually diagonal. And the stiffness matrix, we have 2k from here, and then this would be times, again, look at back over here on the left at this form, so 2k times what would be x, and then minus k times y. Down in the second equation we'd have minus k times x and plus k times y. Once again, the coordinate vector is xy. So these are kind of the systems that we're looking at, and what we did when we talked about the solution was we introduced an eigenvalue problem. So if u and lambda can be found such that k times u is lambda m times u, this is a generalized eigenvalue problem, then we can identify a frequency as the square root of lambda, and as a result we can solve this equation of motion. X here represents the response of all of the coordinates, and it's some function in time, a sine omega t. Again, omega is the square root of lambda, and a v cosine omega t. A and b here are arbitrary constants used to fit initial conditions, times an eigenvector u. Right? So lambda represents an eigenvalue, and u is an eigenvector for this general eigenvalue problem. How do we solve that? Well, we take the determinant of k minus lambda m, set it equal to 0. That's the characteristic equation, and it leads to an nth order polynomial which can be solved, and that leads to n different solutions, right? So remember, an nth order polynomial, so for example a third order polynomial would have terms that look like lambda cubed, lambda squared, lambda, and then constant, and it has n solutions, right? So we have a bunch of different solutions, and we can form solutions for the original vibration system from these eigensolutions. So once the eigenvalues are determined, we can then go back to the eigenvalue problem and determine u directly. Right, so today I want to talk a little bit about some of the properties of u, the eigenvectors. So I want to start off with some motivation, right? Why even do this? Well, I just want to consider a matrix equation, so kx equals f. This is just a general equation. It's kind of related to our system. Notice that kx would be stiffness and spring terms, right? And here I've added in some forcing on the right side, right? So maybe this would be like a static equilibrium calculation if you had constant forcing. But again, this is just motivation for why we want to look at eigenvectors in particular as part of our solution strategies and what we can do with them, really. Obviously, this matrix equation can be solved directly. K inverse times F is equal to F, right? But, you know, the problem is matrix inverses are sometimes difficult to calculate. And even if they're not difficult in the sense that, you know, it's straightforward, there's a lot of work to determine these. It's not the best, it's not the easiest thing in the world, especially by hand, to figure out what a matrix inverse is. So one of the things that we can do is use the eigenvectors in order to simplify the solution of this problem. Now, eigenvectors themselves are not so easy to determine, right? But if we have them, then again we can make use of them. So here, let's assume we have an eigenpair, right? So I have a value of u I. Remember I said there were n of these solutions, lambda, and as a result u. And so I'm just going to take one of them, maybe the ith one. And that's going to satisfy this equation. And in fact, all n of them will satisfy this equation. Now, one of the properties of eigenvectors are that they are linearly independent. So what does that mean? Well, it means that no one eigenvector can be written as a combination of any other. And that's nice, because one of the things that that allows us to do is write any vector in terms of the eigenvectors. So in particular, I'm going to go over here and write x as a sum of all the eigenvectors with some coefficients q. Right? So q1, q2, right, and all the way up to qn times un. So essentially I'm expressing this vector x, which is going to be the solution here, in terms of these known eigenvectors. And I can represent this sort of compactly as the sum from I equals 1 to n of qi times ui. But here, now the unknown variables are qi. Right, so all these coefficients are essentially unknown because I don't know x. Now, if I knew x, right, we can go and find out all of these different q's. But in general, we can write a vector, any vector, as a combination of n independent eigenvectors. So essentially, we're going to change coordinates, right? So change coordinates from x, right, which were the original coordinates of the problem, to instead q, right? So this now becomes a vector of all these different coordinates, right? So basically what that means is that k times x, well, x is q1 u1, q2 u2, all the way up to qn times un equals f. Now, in order to pull off individual equations, right, I am going to pre-multiply by one of the eigenvectors, u. So anytime I do this, I will end up with a scalar equation. And when I carry this out, right, what do I end up with? Well, I basically get q1 here times ui, and I can be anything, right? Anything from 1 to n. I get a q2, and again now this becomes ui k u2. So essentially I'm just distributing this u transpose all the way through this equation. So ui kun, and then this equals now ui transpose times f. And of course we can do this for each value of I, so we end up with n equations. Right? This is basically how we get n equations, n scalar equations, from this change of coordinates. Okay, so at the moment it doesn't look like this would be of much use, right? We started off with n equations and we still have n equations, right? And those n equations could be written as, you know, some matrix A times Q equals G, right? So basically this becomes G, and all of these terms become the elements of A. Right, so that, you know, we'd have another one over here. So again, we can figure out an appropriate matrix times Q1 all the way to Qn equals G, right? And so we can solve this, right? Just like we did formally before. A inverse times G. So kind of the solution here, the solution procedure here is to start off with our original equation, kx equals f, and ultimately we're looking for x, right, which again is, at least formally, k inverse times f. And in order to do that, we're going to go and transform coordinates, right? So we have a times q equals g, right, and all these things are related. And then we'll solve that for q, which is a inverse times g, and then we'll go back, right? So essentially we decompose here our original problem into a different problem in terms of q, right? We solve that, and then we reconstruct the solution. So again, why would we do this? Well, the reason is that in terms of the elements of A inverse may be easier to solve or easier to determine compared to K inverse. Right? I mean, that was the problem up here, right? I said matrix inverses are difficult to determine, right? So I don't want to take an inverse of a huge matrix with a bunch of non-zero elements. But if I can do this in a clever way, and it turns out that using eigenvectors in exactly the way that we've done here is very clever, then finding A inverse is really easy. In fact, A becomes just a diagonal matrix. And so to find the inverse of a diagonal matrix, we just find the reciprocal of all the elements on the diagonal. Right? So again, this is a straightforward but involved problem, and this becomes really easy. So again, what we'll see is that using eigenvectors in this way really simplifies this procedure. Right, so what are the properties that allow this simplification? Right, so recall that both M and K are symmetric when we derive them with Lagrange's equations. Right, so that means that M transpose equals M and K transpose equals K. So the elements on, well, off the diagonal are symmetric. Right, so let's go back and look at the example that we had. M here is definitely symmetric. Both of these are 0. Right, but even K, where they're non-zero, these two off-diagonal elements are the same. Right, so let's consider two different eigenpairs. Right, so we'll denote them by the index I, or the subscript I, and subscript j. Right, so again, looking at this eigenvalue problem, we have k times ui is lambda I times m times uj, and k times uj is lambda j m uj. This is our eigenvalue problem, right, for both of these. So now what I'm actually going to do is pre-multiply this one by ui transpose. Or sorry, this one I'll pre-multiply by uj transpose, and I did write this index is j, and it should be I. While for this next set, I'll pre-multiply by ui transpose. So when I do that, this becomes uj times k times ui equals lambda I times uj m ui, while this is ui transpose k uj, and it's lambda j. So I'm just, working through all this. Notice that these two statements look very similar, except the i's and j's are switched. Right? So I becomes j, and then the j becomes I. Now, one important thing here is that if I look at this, this is essentially a vector times a matrix, well, a vector transpose times a matrix times a vector. So this quantity is a scalar. So what does that do for us? Well, if it's a scalar, then the transpose of that is simply the value itself. Right? So actually, let's say that equals, the transpose of a scalar value is unchanged. Right? So if I looked at, say, 4 transpose is equal to 4. So now, using our rules of linear algebra, right, this can actually be written as U transpose. So basically, I flip the order and I take the transpose of everything. Right, so now X transpose A Y, the whole thing transposed, becomes Y transpose A transpose times X. So since, well, if A equals A transpose, right, then this is equal to A. So that means that this quantity is Y transpose times A times X. So really, if a matrix is symmetric, then when I have this quantity, I can just switch the places for X and Y. So X started off, and then A, and then Y. Now Y starts off, and A, and then X. If A is not symmetric, then I can't do that. Right? But here it is. So as a result, these two statements, well, in particular, these two statements can be written in the following way. UI transpose times K Uj equals lambda I times Uj. Well, actually, let's switch the order of that one as well. UI transpose M Uj. Right, so basically, I just switched the roles of I and J inside these parentheses. Now, this second one is UI K Uj, And now almost the same, except this is lambda j. And then ui transpose m u j. So if I look, the left-hand sides are exactly the same, but the right-hand sides are different, right? Because ui may not be equal to uj. So in fact, if I subtract these two, I see that, again, the left-hand side becomes 0, because this in this are the same. And the right-hand side is just lambda I minus lambda j times ui m uj. Right, so that's actually fairly important, right? Because the right-hand side can only vanish in one of two ways. Either I is equal to j, so we're dealing with the same eigenvector here. But if they're different eigenvectors, and in particular if lambda I is not equal to lambda j, then this quantity is not 0, which means this is. So ui transpose times m times uj is equal to 0. And again, now going back up to, say, this expression, right, or this expression, what that also implies is that ui transpose times k times uj is equal to 0. So that's pretty important, because this, in some sense, is like a dot product, right? And I'll show that in a second, right? But what we would say is that if lambda I is not equal to lambda j, so if these eigenvalues in particular are different, then ui and uj are orthogonal, right? Or in some sense perpendicular. With respect to m and k, right? So with respect to m, with respect to a, or k. So this is going to be a really useful property for us. We've seen this idea of orthogonality before, right? So let's generalize these two just a little bit. We have u transpose m times u and u transpose k times u. So let's write for a general matrix u transpose x a times y. Now this is equal to a constant, right? Because of course here we have kind of a column, or sorry, a row vector times a matrix, right? And then times a column vector. Right, so this is equal to a scalar. Now, it may not be obvious, but the dot product, the standard dot product, can be written in this way. Right, so we can write x dot y as x transpose times y, which we can always throw an identity matrix in there, right? So this could be written as x transpose times the identity matrix times y. So this form with a equals I, the identity matrix, is the standard dot product. That we've all learned about. Now, if we choose instead a to be equal to m, then we have what's known as the kinetic energy inner product. So that's the name we give to that expression, x transpose times m times y. Likewise, if we choose A to be equal to K, then we have the potential energy inner product. And we can use these, in particular the kinetic energy inner product, to help us define the eigenvectors. So now I want to remind you that eigenvectors have arbitrary magnitude. So what that means is the length is unspecified. It's only the direction that is important for an eigenvector. That's pretty easy to see. So let's imagine that I have an eigenpair, lambda and u. Right? So this is some eigenvector that we have found. Right? So really what that means is that k, slide that over a little bit, k times u equals lambda m times u. Okay, so this certainly holds because we've chosen lambda and u to be eigenvectors. So what I'd like to do actually is pre-multiply by some arbitrary constant. Just call it ci. And what I can show is that ci times u is also an eigenvector. So really, I'll just distribute that constant inside. Right, so we get k times cu equals lambda m cu. So if I compare this expression to this expression that I had with just u as an eigenvector, we see that c times u plays the same role. Right? So k times this quantity equals lambda times m times the same thing. Right? So what that means is that ci times ui is also an eigenvector. So if I have an eigenvector, I can scale it by anything, any constant, and it remains an eigenvector. In fact, I don't even have to scale it by a real constant. I can choose a complex constant. So how do we choose the length? Well, essentially, how do we normalize the eigenvectors? How do we make them definitive? We have a couple of choices. We've already seen one. Right? So one choice that we might have is choose one element to be equal to 1. And this is what we did previously when we were solving for eigenvectors. For example, we set u1, so the I1 is the first element of the ith eigenvector, equal to 1, and then we solved for the remainder. We would solve for ui2 and 3 and all the rest of the elements of the eigenvector. Right, so this is one way of essentially specifying an eigenvector. Right, so another thing that we could do here is let each eigenvector have unit length. Right, that's a convenient normalization. Again, completely arbitrary, but let's just let it have unit length. So we would find the eigenvector and then we would scale all the elements so that the total length was 1. Now there's a third one that ends up being relatively convenient for calculations. So choose the length of the eigenvectors so that u transpose m times u. So again, these are the same, ui transpose m times ui. So this would be the kinetic energy inner product of the eigenvector is equal to 1. So how do we do this? Well, if ui is an existing eigenvector, so actually I'll put a little star up here just to denote the fact that this is a specific one that we have found. So what do we know? Well, we know that ui star transpose times m times ui star. We can calculate this. Don't know what it is, right? But it's going to be some number. Call it alpha. So now consider an eigenvector ui is equal to some constant times that original eigenvector. As a result, we see that when I calculate the kinetic energy inner product, as seen here, essentially that's just c squared times the original length, well, the original value of the inner product. So I can choose ci to be 1 over the square root of alpha. And as a result, this quantity is equal to 1. So what that means is that ui transpose times m times uj is equal to delta ij, where delta is known as the delta Kronecker, and it's equal to 0. In fact, if lambda I is not equal to lambda j, and it's equal to 1 if lambda I equals lambda j. So moreover, we can show that ui k uj, which was equal to lambda I times ui m uj. Again, you can look at the eigenvalue problem, pre-multiply by an eigenvector. Well, that's going to be equal to lambda times delta ij. So this equals lambda if I is equal to j. And so ui transpose times k times ui is equal to the eigenvalue itself. So if I normalize by the kinetic energy inner product, then the potential energy inner product of the eigenvector itself is simply the eigenvalue. Let's go back and look at that motivational example that we had. It was basically like static equilibrium problem, for example. Kx equals some F force. I expanded x in terms of the eigenvectors with these unknown coordinates q. And then when I substitute that in, I end up with q1, q2, and so forth. Well, what we've just now shown is that most of these are equal to 0. Right? So here, ui k times x is equal to sum from j equals 1 to n of qj, right, so that's these individual coordinates, times ui transpose k and then uj. So essentially we're just summing over the q1, u1, q2, u2 represented by j. So now the great thing is this equals 0. If I is not equal to j. And here we're assuming that the eigenvalues are all distinct. So all the lambdas are different. And as a result, this equals Qi Ui transpose K Ui. And of course, this was equal to Ui transpose F from the right-hand side. Right, so basically, this left-hand side reduces down to a single term. So we can solve this. In particular, Qi is Ui transpose F divided by this, which of course depends on how we normalize the eigenvectors. And therefore, reconstructing the solution, x is equal to the sum from I equals 1 to n of all of these Qi's, which we just solved for. I equals U transpose F divided by U K times U times the eigenvector. Right, so again, using these eigenvectors, we're able to easily solve for all of these Q's, and then we can go back and reconstruct the solution from this expression. And it's given down here. Right, so in this case, the eigenvectors make that calculation of essentially A inverse back on our motivational slide really simple, because here A simply becomes diagonal. So those are some of the properties of eigenvectors that we will use going forward, in particular when we look at general forced multi-degree of freedom systems in the context of modal analysis. So that's it. Thank you very much, and I'll talk to you soon. Bye.